Yep. Let's start, I guess. So, I didn't change the name of the slides, but I hope it's okay. Today's lecture will be about AlphaZero and AlphaGo and everything connected with it in reinforcement learning. So let's for start talk about some RL till there. What is it? What was on the previous lecture? So let's take a look at this diagram. This what I would like to call a bird's eye view of the reinforcement learning. It considers the core concepts into one feedback loop, which we discussed on the previous lecture. If you deeply understand this diagram, you're already most of the way grasping how RL systems are structured. So first of all, we have at the top of the diagram is agent. The agent is the core component of the core learning and decision making component of reinforcement learning. So the agent learns three key things. It's a value function, V, that means how good it is to be in a state. Yeah, it's a function that takes as input some state from set of states in our environment. Also, we need action value function, Q, that takes state and action that makes agent. That means how good it is to take a specific action in our state current. And policy P, usually you can find P, A, and S. So it's some strategy that defines the probability of choosing action A in some state S. So the ultimate goal of the agent is to find some policy pi that maximizes expected cumulative reward over time. So we can write our decision process as some sequence of estimation, some actions which we takes in some states. So we just want to maximize this estimation. There are two main ways the agent can learn its policy and value functions. It's planning and reinforcement learning. So planning is more model-based, and reinforcement learning is a model-free approach. So let's explore each one. Planning assumes that agent has access to a model of the environment, either provided or learned. This model predicts the next state, and reward given to current state and action. With this model, the agent can simulate future interactions and plan its strategy. This includes solving Gammon equations, sampling trajectories, for example, in Monte Carlo tree search or Zuna. We would discuss Monte Carlo tree search in the end of our lecture today. And this is sample efficient, but depends on the accuracy of the model. So the bottleneck of this approach is model. So let's just throw out the model, and we got reinforcement learning. In contrast, model-free reinforcement learning means the agent learns directly from experience without relying on an environment model. So each interaction yields a transition of the experience. So the agent uses these transitions to update its knowledge using methods such as TD learning, like Q-learning or SARS, any Monte Carlo estimation, and policy gradient algorithms like reinforce, PPO, and so on, and many actor critics models. This approach is more robust to modeling errors, but often requires more interactions. Also, once the agent has learned some estimates or a policy, it needs to decide what action to take. There are two main strategies, greedy or exploratory algorithms. Greedy means we just pick the best known action. So action would be Rmax of our function Q, our action value function. Or exploratory include some randomness to discover better action. So we don't just took the action with the max action value function number, but we want to take some random actions. Exploratory strategies include some epsilon greedy with small chance of random action, or maybe a softmax or Boltzmann exploration, or some entropy regularization in gradient, in policy gradient methods. Also, the experiment returns some feedback as a result of agent actions, next state, and some reward from reverse function. This feedback forms the experience tuple, our current state, our current action, reward, and next state. So depending on the method, the agent, I hope, yeah, everything is okay. So depending on the method, the agent directly updates value functions or policies, or uses this to train or improve model for playing. So agent acts based on the current policy, observes the next state and reward, and uses the experience to improve. So understanding this flow, agent, action, environment, feedback, and learning is the key to understand RL as a whole. All right, let's take a closer look on one of the most fundamental classes of algorithms in reinforcement learning. It's policy gradient methods. So far, we have seen methods that learn value functions like VOQ and use those to derive a policy. So we learn functions and we got policy. But with policy gradient, we flip the script a bit. The core idea here is that we want to train the policy directly. We're not trying to estimate how good each action in a state and there act greedily. Instead, we define a parameterized function, a policy that maps from states to probability distributions over actions. We denote this as written here in formula. So it's P that took some probability and theta, and equals to just this probability. This tells us the probability of taking action in a state S under the current policy parameters, theta, Yeah, now typically theta will be the parameters of our neural network, because we are talking about neural networks. So our goal to optimize those parameters such that the expected cumulative reward is maximized. You might be wondering, why make the policy stochastic? Why not just output one best action deterministically? That's a great question, but there are two main reasons. First, exploration. Stochastic policies helps the agent avoid getting stuck in the local optima early in the training. So if the policy is always deterministic and starts in the suboptimal, which it probably will, it may never discover better action. Second, and this is more technical, we want to be able to compute gradients of the expected rewards with some respect to the policy parameters. And that turns out to be a lot more straightforward when the policy is stochastic. So by training a stochastic policy, we keep our PAS not strictly between 0 and 1, at least initially. This ensures that all actions are considered and that we can explore and learn properly. In practice, how do we implement a stochastic policy? Usually, we don't try to directly output probabilities from the neural network. Instead, we just let the network output row scores for each possible action, also called logits. Then we pass these logits through a softmax function. This function transforms the scores into proper probability distribution. So PAS would be some frag with the, I hope you know, formula of softmax. So that means that during training we essentially just optimizing those raw scores, and softmax handles the normalization. Yep. So this setup is fully differentiable, which makes it very friendly for gradient-based optimizations methods like ADAM or just SGD. Alright, now we have seen how parameterized policy looks like. Let's dig deeper into how we actually train it mathematically. So this is where the policy gradient theorem comes in. It gives us a way to compute some gradients of expected return with respect to policy parameters. Let's start with the optimization objectives. We define J as expected return under policy phi theta, typically starting from some initial state S0. Our goal is to maximize this objective by updating our policy parameters theta in the direction of the gradient. Okay. So this is standard gradient ascent step, which learns our rate, which using learning rate alpha. But the core question is how do we compute our nabla theta, so this part. Here is central result. Let's break this down. So this would be a gradient of the expected return. The outer sum of our states weighted by how likely they are under the current policy P, So the inner sum of overall our actions weighted by some expected return. And finally, this part gives us sensitivity of the policy output with respect to its parameters. So, in simple terms, this expression tells us increase the probability of the action that lead to higher reward. So, and that's it. That's the core intuition. Now, here is a catch. This term, probability of our state is under policy under strategy pi. The distribution over states under policy pi is very difficult to compute analytically. But thankfully, and this beauty of RL, we don't need to compute it. Instead, we just let the agent play. As it interacts with the environment following policy, it naturally visits states in proportion to our probability. So we can use its trajectories as samples from this distribution. This is why we often say just let the agent play and learn how it would be experienced. This idea, learning from on-policy samples, and thus underlies reinforce and many actor critics algorithms. So, let's start from the algorithm reinforce. It's, I guess, one of the simplest and most elegant policy gradient algorithms. It's a policy-based method. That means instead of learning for value functions like Q-learning does, it learns as above some stochastic policy directly. So let's start from the policy gradient we saw earlier. This one. You can see this the same. Now, as we already discussed, these expressions, the expression involves expectations over states and actions. But it's hard to compute this exactly. We don't know probability and we don't know the true QP on our state and action on the step T. So what can we do? Well, we can rewrite the entire expression as the expectation under the policy. Here. This means if we sample states and actions by simply running the policy in the environment, we get data that reflect this expectation. In other words, just let the agent play, collect experience, and use that the estimate the gradient. Now here's the practical trick. Instead of the full expectation of all our actions, we can just plug in the actual action AT take during the rollout or our play and the associated reward or return. That's what leads to the reinforced rule. The stochastic gradient ascent update becomes like that. Here, what we have. This is some learned approximation of the action value function, usually like the actual return observed from the rollout. This null operator is computed analytically through backpropagation, and alpha is our learning rate. In this reinforced algorithm, we typically use Monte Carlo estimates of returns to approximate our Q function without using any critic. That makes the method simple, but also high variance. We will address that in the next slides. Let's take a brief historical detour. Here starts our more historical part of the lecture and less technical. So let's talk about, I guess, one of the most important early milestones in reinforcement learning is TD Gammon. TD Gammon was developed in 1992 by Gerald Tesaro in IBM. It's just a computer program designed to play the game of backgammon, and it became famous because it was one of the first systems to combine reinforcement learning with natural networks. And it works surprisingly well. Unlike traditional game AIs of the time, which uses handcrafted rules and search trees, TD Gammon learned how to play purely by self-play. So playing games against itself and improving based on the outcomes. So this idea is important, that TD Gammon didn't know how to play this game, he just learned it by himself. So the key information was using temporal difference learning. So TD Gammon means temporal difference. It's combined with a simple neural network. So at the bottom we have 198 input units, which represent the current board state or the position of the piece. Then a hidden layer of 40 or 80 neurons, nothing huge, even 90 standards. And at the top, the output, it's a single value representing the predicted probability of winning from the current state. So the system uses TD learning to update its weights, and idea that TD error would be some value function, which value function on the state as t+1 minus value function on the state as t. So if the outcome turned out better than expected, the weights were adjusted to increase the value of the current state. If it was worse, the value was decreased. This is bootstrapping. We're using our own prediction to help improve our predictions. What made this remarkable was not just the method, but its result. TD Gammon learned to play at the level of strong human experts without being especially taught the rules of strategy or tactics. Just from raw self-play and TD learning, it learned sophisticated positional strategies that even surprised human experts. This was a wake-up call for all AI and ML communities. Even shallow neural networks plus some reinforcement learning can produce expert-level behavior without any explicit symbolic reasoning. So let's cover to the core principles like policy gradients, value functions, and model-based learning. Let's take a step back and look at the big picture. This diagram represents like high-level taxonomy of reinforcement learning algorithms, categorized by how they approach the problem of decision making. At the top, we split in the two biggest parts. It's a model-free reinforcement learning and model-based reinforcement learning. So that means the agent learns how to act without building an explicit model of the environment. Here, the agent learns or uses a model of the environment, some function that can simulate outcomes. Model-free methods are split in two big categories. It's policy optimization methods and Q-learning. some of the most well-known methods using policy gradient we discussed above. A2C and A3C, it's actor-critic methods that synchronous or asynchronous parallelism. PPO, so proximal policy optimization, stable policy gradient methods used widely in practice, and TPO, as I remember, it's trust something policy optimization, trust region. Yeah, it's an earlier, more theoretical grounded version. So those methods tend to be more stable in continuous action spaces and work well with the neural networks. Yeah, my ears are tired. Q-learning. This group focuses on value-based methods where the agent learns our value function Q and acts gridly. So popular example are DQN. It's deep Q networks that the breakthrough paper from DeepMind. It's C51, which models the full distribution over returns. It's like distributional RL. QRDQN, it's some version of classical deep Q-learning network. And here, I don't remember what is this algorithm. And they have some common algorithms that uses strategies for both methods. There are off-policy actor-critic methods, blending value and policy learning. Now let's talk about model-based RL. Model-based methods are again split in two. It's learn the model and given the model. Learn the model of the environment, either explicitly or implicitly, uses for planning or policy improved. So, for example, it's word modeling, I2A, it's imagination augmented agents, it's a combination planning with deep networks, and MBMF, MBVA, some model-based value estimation or fine-tuning policies. And sometimes we assume that the model is already given, either fully known or perfectly learned. So, for example, it's AlphaZero, but without any spoilers. We going to the next slide. It's Game Go. Let's talk about the Game Go and its basic rules. What is Go? Go is the ancient board game invented in China 2,000 or 3,000 years ago. It's one of the oldest games still played today, and also one of the deepest and more complex game in terms of strategy. So it's playing on 19 and 19 grid. We have two players, black and white. Takes turn placing stones on the board, and once placed stones do not move. They remain on the board unless captured. The objective is to control more territory than your opponent by the end of the game. So basic rules is turn alternate, black plays first, then white, and so on. A move consists of placing one stone on only one empty intersection of the lines on the board. Here, I guess you can see. Group of stones are completely surrounded with no liberties, are captured and removed from the board. Also, you can't move that immediately repeats a previous board state. This is the KO rule. You are allowed to pass your turn, and the game ends when both players pass. Then territory is counted. So there isn't like end of the game, I guess. Why go hard for AI? Go is a dream and a nightmare for AI. Because like in chess there are about 40 or 30 legal moves per turn. In Go it's close to 200, so it's in 4 or 5 times more. And we need to think that the complexity of the movements will rise up in the exponential. So the number of possible board position in Go is estimated like 10 prime 200. That's more than atoms in our universe. Also, classical search techniques like min-maxing struggle because for branching factors is so high, and because the reward is extremely sparse, you only know if you won or lost at the game. Learning is difficult. Because, by the way, you didn't get you are losing or winning the game. Now we seen how complex the game of Go is. Let's take a look on the evolution of the AI programs that have tried to play it. The first serious attempts to program a computer to play Go began in 60s. In 1968, Albert Zobris created one of the earliest Go program. Those programs could only play on small boards like 9 by 9 or 13 by 13. A full 19 by 19 board was far too complex for computation resource of the time. And the early systems were limited by both computational power and algorithmic simplicity. They relied heavily on handcrafted rules, patterns recognition, and basic evaluation functions. But despite their limitations, these early efforts laid the groundwork for decades of future research. In the 80s, 90s, we saw gradual progress, primarily thanks to increasing processing power and improvements in general AI techniques. So researchers introduced more advanced heuristics, pattern databases, and search strategies. Programs such like Galaf or Go Intellect, Handtalk, and Gourmet emerged. So these engines could analyze board position more intelligently and even beat beginner human players. But, and this is important, none of them came close to professional strength. In fact, even the best Go programs in the 90s played at about the level of weak amateur and only on the small boards. One of the big breakthroughs came in the late 90s and early 2000s with the development of Monte Carlo methods for Go. Monte Carlo Tree search is a statistic sampling based approach for planning, and we talk about the future. And by 2K6 and 2K10, so these MCTS based programs reached done level strength, so it's a competitive amateur level. Now let's take a closer look at how strong or weak Go programs were up until the deep learning revolution. Here we can see some key moments in the evolution of computer Go performance. In 1997, Janice Kim, a professional Go player with the first Dan Pro, played against the program Handtalk and won, even with a 25 stone handicap. That's an enormous advantage, basically giving the AI a huge head start, and yet she still won. The same year, Handtalk beat a group of young amateur players aged 11 or 13 years with ranks between 2nd or 6th dan, but it still needs an 11 stone handicap. In 2K1, another program, Many Faces of Go, defeated the Insei, a Japanese student training to become a professional. Again, only with a 25 stone handicap. And in 2K10, at the European Go Congress, Moja TW, a Monte Carlo tree search based program played on the full 19 by 19 board against Katalin Tarano, 5th Dan Pro, and Maga TW had a 7 stone per handicap and managed to win. This was a sign of real progress. So clearly sometimes was changing. Something was changing, but progress was painfully slow, and even the best programs needs some large handicaps to beat strong humans. Now think about this. In 1997, the same year, Handtalk need 25 stone handicap. Deep Blue, IBM's chess engine, defeated Garry Kasparov, the raging world chess champion. So watch such a stark contrast. Why could computers dominate in chess but struggle in Go? What you can see here is the schematic representation of game tree with all possible computational continuations that can arise from just a few moves in a game of Go. So each node of the tree is the board state. Each edge represents a legal move. As you can tell, the tree explodes very quickly. So these positions have this tree. Each of these positions have its own trees. Each of these positions have its own trees, and so on. So after just a few moves, we are branching into hundreds, then thousands, then millions, then billions, and so on of possibilities. That's what we call a combinatorial explosion. In chess, the branching factor is about 35. In Go, it's often over 200, and that happens every single turn. and multiply that across a game can last 200 to 300 moves, and you can get a search space of roughly more than like combinations in Go, more than atoms in the observable universe. This is why traditional brute force search fails. You can explore the full tree, it's too big. You can store it all, it won't fit in memory, and you can't relate every leaf because the reward comes only at the end of all games. Yeah, it's a thing I talked previous. Here we have some difficulties of evaluation. Is the problem that Go is very hard to evaluate. In chess, we can use simply heuristics like material count or king safety or piece mobility. We know really what's the good position and what's not. But in Go, there are no material to count. The value of moves depends on the global board context. And here's the kicker: even at the end of the game, humans sometimes debate who's ahead. So even defining who is winning can be ambitious, especially if territory boundaries are not fully resolved yet. So training a machine to evaluate a board position in Go is an enormous challenge, especially without handcrafted rules. This is the moment everything began to change for computer Go. In early 2Ks, a new algorithm called Monte Carlo tree search was introduced, and it led to massive improvement in Go playing programs. Let's unpack how it works. The idea is beautifully simple. Instead of searching the whole tree, sample random games, we would call simulations or rollouts, from their current hour position, see what works well and prefer those branches next time. So over time, this creates a search policy that focuses on promising actions while ignoring weaker ones. This is very different from traditional alpha-beta search, and this method consists of 4 case steps, which you can see here is selection, expansion, simulation, and backpropagation. Selection. We start at the root of our search tree and follow a path down, selecting child nodes based on the policy, often using like upper condition bound or booked in AlphaGo. At this point, the algorithm is exploring what is already known. So it's picking some actions that have done well in previous simulations. When the selection phase reached our leaf, this one, a state that hasn't been explored, we can expand the tree by adding one more new child node representing possible next action. This is the phase where the tree actually grows. So it's not grows exponentially, it just grows by one leaf. Now comes the stochastic part. From new expanded node, we simulate a full game to the end using some simply rollout policy, sometimes completely random, sometimes with some heuristics. At the end of simulation, we record whether the game was a win or a lose. And finally, we backpropagate the result at the simulation up the tree. So every node on the path that led to the simulation is updated. Wins are counted, digit counts are incremented, and the tree statistics get more accurate. So this completes one MCTS cycle. We repeat this process thousands and million times per move, and eventually the most visited node becomes the recommended move. And here's the power. MCTS balances exploration and exploration dynamics. It focuses its search on the high potential moves without needing a perfect evaluation function. UCB1 formula, it stands for upper confidence bound, and it comes from the theory of multi-armed bandits. It's a classical exploration problem. Here's the formula. It's just took the number of wins of our simulation through node Y and takes how many times our node has been visited plus coefficient, it's exploration constant by default square root from 2 times square with the natural logarithm of t, which is the total count of simulations that parent nodes made, and I is the same count of simulation for the node associated with our action. So this formula balances two complete goals. It's exploit what seems good. The first term is just the empirical win rate of action I, and explore what we haven't tried much. So the second term grows large when ny is small, encouraging the algorithm is try like less visited nodes. In other words, if the action seems promising, we keep trying. But if we ignore something, we go explore it just in case it's actually better. And if not, we just go to the another action. Why it matters? This selection rule is allows MCTS to focus search only where it matters. So it's just a heuristic for our algorithm tree search. And this is the moment the world realized AI had entered a new era. Not like previous, all humankind known that AI, ML, there are very powerful parts of the computer science, but this came close us to AGI or something better maybe. In the March of 2016, AlphaGo, developed by DeepMind, now is the Doge company of Google, challenged one of the strongest human Go players of all time, Lee Sedol, a 9-dan professional from South Korea. Before the match, most Go professionals and honestly most AI researchers expected Lee Sedol to win easily. Forecast predicts a 1-4 result, with the AlphaGo winning only one game at the best. Why? Because no AI had ever come close to beating a top-level pro on a full 19 by 19 board without any handicap. And Lee himself was confident, saying, "I believe I will win maybe like 5-0 or 4-1. But what happened shocked the entire Go community and AI researchers and the whole world. The final score was AlphaGo 4 and Lee Sedol 1. AlphaGo won the first 3 games in a row. This match marked a turning point in public and scientific perception of AI. It proves that AI can master highly intuitive, strategic tasks, and learning by self-planning can surpass centuries of human knowledge. Now let's walk through the timeline of AlphaGo development from lab project to world champion. It was developed by Google DeepMind in 1415 by David Silver, Ajay Huang, and many others. The goal was clear but incredibly ambitious. Built an AI that could play Go at a world-class level using deep reinforcement learning. The first major test came in October 15 when AlphaGo played against Fan Hui, is three-time European Go champion. AlphaGo won the match 5-0, so it's clean sweep. And this was the first time in history that a computer beat a professional player without handicap on the full board. Fan Hui was stunned. He later became a collaborator with DeepMind to help explain AlphaGo's style. Next was in January 2016, DeepMind published a paper mastering the game of Go with deep neural networks and research. This paper became legendary. It describes how AlphaGo combined policy networks, value networks, and MCTS to search efficiently. And the big match is Lee Sedol. Then came the famous match, as we talked previous. As we discussed, AlphaGo won 4-1, defying all expectations, and the world was watching. Literally, millions turned in to watch a Go match, something unheard of before. And the final boss was in 2017. AlphaGo faced KG, the world's first ranked player at the time. This was a 3-game match in China. KG played extremely well, trying everything, including mimicking AlphaGo's own style, but AlphaGo won 3-0. After this match, DeepMind retired AlphaGo, releasing a paper and announcing they would be now focused on more general purpose AI, leading to AlphaZero. But we want to know what is inside AlphaGo. There was the initial network training to imitate human play. So the SL policy, SL means supervised. So supervised learning policy network takes the current board state as input and outcomes a probability distribution over all legal moves. So this tells us given board state, how likely is a human expect to play move for action. The network is a deep convolutional network, which with a 13 layers. The training data was massive. AlphaGo was trained on 30 billion positions from human expert games, professional level data. From that, it saw 30 billion board move pairs during training. The supervised learning policy network could predict the next move of human pro with 57 accuracy, which is very high for this task. And that might not sound huge, but it's extremely strong. Pros often disagree with each other, and even top engines today rarely reach that level of imitation. And also AlphaGo also train a second weaker policy network denoted PPI, with a smaller accuracy, but inference time is much less. So with 3 milliseconds per one step to 2 nanoseconds. Next. Previously, we saw how AlphaGo learns to imitate human players as supervised policy network, but imitation can only take you so far. To go beyond human level player, AlphaGo needed to improve their playing against itself, and that's where reinforcement learning comes in. So the second major component is the RL policy network, which is trained using self-playing reinforcement learning. It uses the same 13 layers CNN structure as the SL policy network, but instead of learning to imitate, it now learns to maximize its own win rate. And crucially, it is initialized with the weights of the SL policy network, so it already has a good starting point. We can talk about learning procedure of this network. So AlphaGo plays games against itself using the current version of the RL policy network. After each game, it adjusts the network weights to increase the probability of winning moves. And this is stands policy gradient reinforcement learning. Using Monte Carlo returns as a reward signal, it repeats this over a million of games, and learning strategies to human has taught it. This is where the magic happens. AlphaGo begins to discover new tactics, new shapes, and new ways to win. And the RL policy now becomes much stronger there. RL policy network becomes much stronger than SL policy network, and it won 80% of games against SL policy, and also it beats Apache, one of the strongest open source MCTS based Go engine, so 85% of the time. And here's another kicker. These wins happened without using any MCTS at all, just the raw move predictions from the policy. And now comes the third and major piece, the value network V theta S, which estimates how good a position. So, the value network takes a board state as input and predicts the single number. It outputs the probability of winning the game from that position, assuming both players play optimally according to some learning policy. In other words, it's like a Go intuition engine, helping AlphaGo quickly assess how good a board position is without playing the end. It used the same structure as both policy networks, but instead of outputting the move distribution, it outputs a scalar value between 0 and 1. And this is trained using regression, not classification. Also, they couldn't train on expert games. There aren't enough of them, and outcomes are often too deterministic. Instead, they use games generated from self-planning with the RL policy network. And the target label is simple: 1 for win, 0 for lose. Over millions of games, the value network learns the estimate long-term winning probability from a statistic position, something that was previously possible through deep simulations. Here comes the last part of AlphaGo, is where the search means learning, where neural networks are embedded inside Monte Carlo tree search to make decisions. So at each step, AlphaGo builds MCTS like tree rooted at the current board position. As the classic MCTS, it repeatedly selects promising paths, expands the tree, runs simulations, and propagates the result. But unlike traditional MCTS, which relies on rollout and hand-coded heuristics, AlphaGo uses learned components. When expand a node, AlphaGo doesn't treat all actions equally. Instead, it uses the SL policy network to bias the tree expansion towards permission moves, and this acts as a kind of prior probability. So focus search of the top 20 most promising moves out of more than 200. Interesting that it turns out the SL policy works better for tree building than the RL policy. At the leaf node, AlphaGo needs to estimate the value of each position of the board, and here it uses the value network trained via self-playing to predict the expected outcome from the node. But it doesn't stop there. Sometimes AlphaGo combines with a rollout, so it uses fast policy, plays random moves until the game ends, and arranges the result with the value network's prediction. After many thousands of simulations, the most visited child node becomes the next move. So the number of visits as a softmax of action probabilities with more visit indicates higher confidence. After success of AlphaGo, DeepMind asked as a bold question. What if we could make the algorithm general? What if we removed human knowledge entirely and let the system learn itself everything from scratch? That's how AlphaZero was born. So it's a general reinforcement learning system. It can play Go, chess, and shogi using the exact same algorithm. It doesn't use human data, doesn't imitate expert moves. Instead, it learns purely from self-playing. So key point is was introduced in the paper Mastering Chess and Shogi by Self-Playing with a General Reinforcement Learning Algorithm. So AlphaZero trained on the prior data, beat AlphaGo 0 in Go, beat Elmo at Shogi, and beat Stockfish in chess with 28 wins, 72 draws, and 0 losers in a 100 game match. Each game was learned from scratch using only the rules of the game. So, what's inside AlphaZero? Instead of having separated SL policy, RL policy, value network, and rollout policy, AlphaZero uses a single neural network denoted F theta that outputs both the policy and the value. So the probability distribution of the legal moves and the estimate of the expected outcomes from the position. This network is used to guide MCTS search, evaluate a leaf node, and train itself via reinforcement learning. Yeah. And Let's now look at what AlphaZero minimizes during training. So loss would be like that, where Z is the true outcome of the game, like +1 for win, minus for lose, and 0 for draw. V is the predicted value from the network. Pi is the MCTS improved policy. P is the network's predicted policy. C, as previous, is the regularization coefficient, and theta is the weights of our neural network. So the loss has three terms. It's a value loss. It's the first part, policy loss, and our regularization for prevent overfitting for model. So this loss trains the network to play better and evaluate better simulationally. And all of this is learned by scratch without any human games or domain-specific feature. Yeah, so I guess this ends for our today's lecture. We learned about AlphaZero, AlphaGo, how it works, and some about MCTS, Monte Carlo tree search algorithm with the policy algorithms, and I guess, yeah. Thank you, everyone.